Hello there. Welcome to another session in special relativity. So today we are going to explore some of the problems. We're going to do some problems today also, and some conceptual things concerning space, time, in length, time interval, frequency of light. We'll also do something called simultaneity. Sense of whether two events are simultaneous. So it has to do with interval. So if as for example, if two events, time between two events in one frame is 0, then is delta 2 or delta t1 between the two events is 0 or not, so we're going to explore that. Okay, all right, we're not going to drive these. These are Lorentz, these are called Lorentz transformation. We're going to just assume that we are given that relationship of mechanical quantities, right, between two different frames. So relativity is all about physics. What are the relationship between physics in one frame to the physics in another frame? And the frames are assumed to be inertial frames. So if you don't know inertial frames, you should go back to my previous pretty long video, okay? Now, let's just recap. So we have two frames. Both are inertial, so this is at rest, or one is at rest with respect to this absolute rest, okay? And for simplicity, there's another observer which is moving along the x-axis. So rather than a very arbitrary direction, we're just going to pick the direction in which it's moving as x direction, just for simplicity. We can write more complicated formulas, but it doesn't really help. All right, so there is a particle at this point, and you can say if you're in this frame, you can give its coordinates and time, and if you're in this coordinate system, you can get its coordinates and time. Now, first of all, I'm going to say that I'm going to pick the time 0 for both of these. At some point, the way I've laid it out is O2 is right on top of O1. It's moving at steadily. At some point, it's over there. At that point, I'm going to just say this is 0. And we're going to also do this gamma. And sometimes gamma is defined, I'm going to put a u just to denote that there's a velocity that goes there is u. Okay? You'll see why it's important to just, name it like that. In most books, it's just is going to be just gamma. Okay, so the relationship between these two descriptions of this particle is given by this. Okay, so before we can actually make use of this in a more intelligent way, without making mistakes, because there will be a lot of confusion when you use them, especially when someone describes a situation. It's very confusing normally, and you don't really get confused. You need to get some basic vocabulary right. So first of all, what is, like, say, T1 mean by itself? Okay, so just look at one frame. So let's look at this fixed frame. So you have x1 axis, y1 axis, and z1 axis, and O1 is just fixed here. So what we like to have is time. We can imagine that it's not just these 3 points. You can say all this grid. You can have, let's just do xy plane. So you can mark these grids and that gives you the coordinates. So like this one will be some, if you're here, this can here, and this is y1 value for that. But then what we also want to know is what's the time here. So we attach a clock here, and whatever the time here is we call it t1 for that point, whatever is happening at that point, at that instant. But you know, the clocks all over this must be synchronized. This t, and if I had a t here, has to be synchronized. So what is called synchronization procedure, so that you know, these in the same frame, in one frame, they're not out of whack. So the way we're going to synchronize is, let's see, we have x1, y1, and you can have arbitrary point. Let's just, for drawing's sake. So if this is at t0, the clock is here. So if some arbitrary point p at t0, clock here should also read 0. So that's a that's called these clocks are synchronized. But how would we do that? So say at t equal to 0, we send a pulse of light, and this distance is say r. That point is r distance away from the origin. So the time, if they were synchronized, okay, by the time this light pulse comes over here, this should read, I should set it to the time it took the light to get there, right? So time to get the light there will be this r over c, and c is affixed in every frame. So we can use this procedure. So we when the light comes over here in this clock, we will have time set to this value. This time is that value. Then you can say when the light was sent, this would have been this clock. When the light was sent, would have been also facing like this. So when the light was sent from O1. So this way I can do, everywhere I go, I can synchronize it. So we can say when this was 0, at that instant, this guy is also reading 0. So everywhere, all these clocks were reading 0. Okay. So that's a synchronization procedure. So this is called a synchronization. And that, in that sense, we're going to use T1, T2, etc. All right. Now we're going to look at a time interval in one frame versus what happens in the frame. These are the times related, right? But we're going to look at time interval. And what do I mean by time interval? So time interval mean I am at this point. So let's actually use the same ink as over there. So I'm in this O2, and I'm going to look at the clock that's tied with here. This clock is fixed at this O2, and so this frame is moving, so this clock is actually moving, right, with U I hat. So this is the x-axis, x2, y2, and z2 is just coming out. So if you look at this clock, let's see at t equal to 0, t equal to 0. So this is the situation at this point, this clock is pointed up. And when we look at the other, this is O1, and this is Y1 and Z1, X1. So at this instant, we have two clocks which are kind of on top of each other, and we can compare it. So at this instant, so clock at O1 reads T, let's call this incident, say A, at this point, T1 equal to 0 and T2 equal to 0. And the position is everything. Both those clocks are clock at O1 reads T1 and clock at O2 reads T2, and the O1 is at, of course, O1, and this clock is, of course, at O2, and both clocks are O1. Let's see, some time has passed, and this thing is over here, and so there's a clock, that's a second clock, and let's see, we can use the other clock with it over here. So now this clock is let's me write. So there are two clocks now. There's a clock here, and so there is at that location there is a clock here, and we want to compare. They were synchronized. Remember, they were synchronized. So if this is this originally here, and so originally this was here also. So when this clock comes in over here, whatever the time is passed, this is time T2 at some coordinate in terms of X. So this clock in frame O1 is at not origin, not at that place, but at some other place, X1. It's at X1. So this is a separate clock, and that's why I need to synchronize this earlier to compare, right? So I'm going to compare this clock with this clock, and we should be able to tell it. So, and this comparison is what these relations refer to. Comparison. So over here, if you look at x2 equals to is at the origin, so x2 equal to 0. This clock is at the origin, and this clock reads T2. T2 is some time, and because this clock is not moving in this frame, we usually denote by tau. It's called proper time, since this clock not moving with respect to O2. So we can give a letter tau. I want to know what's going to be over here. So the relationship says here is that this will be some reading T1. This T1 will be, if I go look at over here, gamma U, and gamma U is this thing, and T2 is tau, and then x2 is 0. So this is just a gamma U tau. So we are not comparing back to this, right? We're comparing to a new clock. So in this frame, we're saying that time elapsed for the corresponding time when time elapsed was t2 is actually which is gamma u t2, you know. So so t1, so, or you can say, but two clocks. So here is two clocks, not one clock. T1 is equal to gamma T2, and this is one clock. Now, so one clock, this is proper, is equal to gamma tau. And you can see that since gamma is greater than 1, gamma u greater than 1, greater than equal to 1. If you use 0, it's equal to 1. T1 will be greater than equal to tau. So if tau is 1 and is greater than 1, so the time. So we say actually comparing frame to frame now. So time in frame, so-called proper time in frame 2. That's the way we have set it up. Proper time will always be less than time elapsed in other inertial frames. Okay, what if I wanted to not compare this guy with this new clock, but I wanted to compare with what's happening over here? So if I want to have one clock to one clock, if I want to have one clock to one clock, you can see that what I have to do is when it's over here, I will need to send a light signal back to here. So let me erase and come back. Okay, so we want to have this clock, keep an eye on that clock, and when time is t2 over here in this second clock, second frame, from the origin of this, so x2 equal to 0, from origin of this we emit light, and it's going to take some more time to come back, and that should be equal to whatever the distance this is, x1 over c. So the time originally when they were together, it was 0, so that event was A, and then it come back, the signal come back is B. So TB in frame 1, TA in frame 1 was 0, just when the clock had left, his frame was moving to the right. So this is moving to the right, so TB1 will be this T1 moved over there, what I saw compared with that, plus I have this delta T, and that together is gamma T2, and delta T is x1 over c. So what's this x1? X1 will come from here again, just using this. X1 is going to be gamma, I'm just going to use gamma, not gamma u or something like that. This is 0 plus u t2. So we can see gamma t2 plus gamma u over c gamma t2. So 1 plus u over c gamma t2. And let's see, I can simplify further. 1 plus u over c, and gamma is square root of 1 minus u square over c square. Well, I can actually write this guy as 1 minus u over c, 1 plus u over c. So this under the square root, so this will become this, and that's t2, and so this is square root of 1 plus u over c, 1 minus u over c, t2. Again, when I compare, so the t for this, when the object is here, so I'm going to compare with this clock itself. Okay, so then now this t, let's call it t1 1 clock. This is the clock at origin at 01. In that clock, for when the time in the second clock was t2, I will record it as square root of this thing, square root of 1 plus u over c, 1 minus u over c. I could simplify more, but I just leave it like that, times t2 and 1 clock. So this actually is very important, and that goes into what frequency of light. Okay, so I'm going to, so there are two different time dilation formulas you can get. So you can see this t1 at 1 clock, t1 2 clocks is always getting t2 1 clock at O2, right? So this is the proper time. So always going to be greater than equal to that. That's one observation. But even for 1 clock, if I want to say what's happening over my origin compared to what's happening at the origin of that, so how much time t1 1 clock is equal to t2 1 clock at 01. So you can see in both scenarios the time in this rest, when the clock moving, the moving clock runs slower, right? Moving clock. So we can say a moving clock runs slower. Often says it runs slower. And this is behind that twin paradox. It's just a paradox, and it's not something we can't resolve. Okay, I'm not going to talk about that now, but you can read on twin paradox yourself. So this is whether I compare with this clock at the origin to the clock at the origin, I compare this clock at the origin of the second clock to the frame, meaning clock here when it's here, clock here when it's there. So in both these scenarios, the time in one frame will be different than time in the other frame. Okay. Time dilation refers to this formula. This formula is called time dilation. Now this formula is used to actually relate the frequency of light in the two frames. So I'm going to just jump to the frequency light. I'm come to the length a little bit later. Okay. Okay, so we want to relate frequency in the two frames. Frequency of light in two frames. How do we relate frequency of light in two frames? Well, so suppose this is my frame 2. Okay, this is frame 2. Frame 2, and this is x2, and this is y2, and this is z2, and these are wave fronts. So this this was say emitted at t0, say this was at t equal to 0, let go, this is t equals to 1 period later, that's t0, t equals to 2 period later, and so on and so forth. So the way we would look at this is, of course, t equal to 0, we're going to have them right on top of each other. So we'll have clock in both of these. So there are two clocks. So there's a clock for the frame 1. So this is O1 clock, and then we have a clock for the O2 clock, and both are at 0. Okay, so when and this guy is going in the x direction with speed u. So now at some other time, this clock is for so this t equals 0, so it will correspond to when this guy gets emitted, and this clock is going to read t0, so t2 equals to t0, right? Now I need to compare this signal will have been at some point x1 along this x-axis, common x-axis, x1, and so this x2 axis, common x-axis, right? So at this time, I'm not comparing this time to another clock over here, but I need to come back here and compare to this clock. So when would this wavefront will actually reach over here, right? So this is x1 over c delta t later, right? So it's exactly like this. So that when it comes back over here, delta t over delta t in the original frame, or delta in the rest frame, was equal to t0, but delta t in this one, I'm going to compare with the same clock. So delta t1 is 1 clock at O1 equals to somewhat delta t2 1 clock, and this will be t0. So that will be the relationship, and this will be, I already know, 1 clock to 1 clock comparison, and that's going to be 1 plus u over c 1 minus u over c t0, and so this will be the time period. So this will be the time period in clock 1. This was the time period in clock 2, in the frame 2, which is the rest frame. So we're just gonna call it t0, right? This is in the rest frame. The emitter is attached to the origin and is moving with the origin of the second frame. So this is the time period between this. So frequency would just be inverse of that. So frequency in 1 will be a square root of 1 minus u over c over 1 plus u over c frequency in the frame 2, which is the same as rest frame. This is same as rest frame frequency. Now let me say something about this formula here. Okay, so you can because this moving to the right, u is positive, right? So just separating. So this is greater than or equal to f2 if u is positive. That means they are moving away from each other. moving away. Actually less than, just noticed numerator is that, so it's less than equal to that. And this is called red shifting, because frequency getting is smaller, right? And is greater than equals to f2 if u is less than equal to 0, which means they so you had one frame, and the second frame, if you use negative, then it's moving this way. So that's the case, and this is moving away like that. So that's the case. In that case, moving towards O1, and so this will be called blue shifting. You can also write this in terms of the wavelengths they will see. What's the relationship between the wave? You know the wave formula, f frequency times wavelength is the speed, and c is same in all frames. So you'll have a f1 lambda 1 is c is f2 lambda 2. So you can see from here that lambda 1 will be f2 over f1 lambda 2, and so this will inverse 1 plus u over c, 1 minus u over c lambda 2. So if you have this situation is moving away, that means this is 2 and this is 1. Lambda 1 will become greater than equal to lambda 2, and then that's if you look at the spectrum, about 700 nanometer is red, and about 450 nanometer is blue. So that now you know this is why this will be red shifted. So the difference between them is called the red shift. And so another situation will be in this guy is moving towards O1, then lambda 1 will be less than equal to lambda 2, and so this will become blue shifted. And this will be red shifted. Okay, so, and this is the relationship between frequencies and intervals. So we talked about intervals, we talked about frequency, time, space. Now we want to talk about length. Okay, so what is the meaning of length? Let's look at one frame. Just say any one of these frames, say frame number 2. We will attach it to the frame number 2 again. So suppose we put a meter stick, some length L0. So this is x2, and this is z2 and y2, and so it's kind of attached to this, but it will move with respect to the other. But over here it's a rest frame. So say ruler at rest with respect to this O2, with respect to O2. So it's not moving, so this is a rest frame. But this frame would be moving in the x direction as before, right? So this guy, the entire thing is moving with respect to u I hat, with respect to this with u I hat. So the meaning of length, just looking at this, the meaning of length means find the coordinate here. So said this end is A and this end is B. So x of A in second frame and x of B in second frame. But we want to find these two at the same time. This is very important, okay? So we want to find this at t2 equal to 0 and t2 equal to 0. So we want to know these coordinates at the same time in this frame. At the same time. So xb2 minus xb1, that's the length. So length in 2 is going to be this. By knowing where right end is at t equal to 0 and where left hand is t equal to 0. So that's the, so let me write down x right end at t equal to 0 minus x left end at t equal to 0. So that is the definition of length. So what's the length in L1 will be? Length in L1 will be, with respect to this, will be, I need to find the coordinate of B, x of B in frame 1, x of B in frame 1, when say t1 is 0, pick a t1 0 minus x of A in one frame when t1 is 0. So this will be the length, and that's the length in the 2. And I want to know what L1, let's call it L2, how L1 and L2 are related. I will prove to you that L1 is actually L2 over gamma u, and gamma u is this. Okay, so length, this is why we say that means L1 is less than equal to L2. That means the proper frame length will be the longest. So this is the proper frame because it's length in the proper frame. Why do we call proper frame? Is because here the metric stick is at rest, where metric stick is at rest will always be greater than equal to length of the same object in any other frame. Or equal to in any other frame. So this I want to show this. Another thing that will happen is if you had a box like this and you have a width, then the width would not be affected if the movement is along x-axis. Then the y coordinate and z coordinates are not affected. Okay, which is kind of very clear from just the way transformation works, right? So let me now show how to relate this, how to get this relationship. Okay, and it's because there's some confusion when people do this, because you got to do it at the same time. All right. Okay, so we are going to do length now. So to do length, let's place a metric stick right at the attached to the second frame. So metric stick attached to the second frame. Attached to O2, and along the x-axis is the movement. So we're just looking at the x-axis right now. Okay, so you look at this, we call it events, right? So A, the left side, at this instant at t equal to 0, t2 equal to 0, you have these in the second frame of the left side, and this is on the frame 01. These are the values for the left side, and for the right side you have these values, so that the length is L0 and t2 is 0. So because this is same, I can tell the length is L0. Fine. Now we want to convert this to get what this event will look like in frame 1. So when you convert that, you will get, actually t1 will not be 0 for corresponding to that. So let's look at this guy. So t1 corresponding to that will be, of course, t2 is 0, then it's going to be like that, gamma u times u over c square L0, right? But I want to get the length in 1, I want xb1 when t1 equal to 0 minus xa1 when t1 equal to 0, right? So we want both at t1 equal to 0, but this I'm getting from this, I'm getting t1 not equal to 0. So let's look at what x1 will look like. X1 will be, now this is 0, so the gamma u x2 is L0. So clearly I'm getting this x1 value, which is for a later time in t1. So xb1 that we want is actually earlier time. So xb1 will be what I got, x1 minus ut1. So I'm going to have to subtract it because I want to go earlier. So this point would have been somewhere earlier. So now this would be gamma u L0 minus u square over c square gamma u L0. So if this is 0, x1 0, so I put this in here. So length in L1 is gamma u L0 times 1 minus u square over c square, and this is gamma u, so this is equal to gamma u L0 1 over gamma u square. So that's how you get L0 over gamma u, because we are looking, the length is defined as where the two things are at the same instant time in that frame. So that's for the length. Okay, so let me do some problems. I want to go take 5 minutes or so to do some problems. Okay, so here's a typical problem that uses the formula that we have derived. So one of the things to notice is many times you think of this as the moving frame. So here it looks like O1 is moving, O2 is moving. No, how do you say it? Okay, so we always, it's really easy if you think the way we have been doing the derivation is the fixed one, you just keep it at 2. So this is the 2, and the other one you just, so the formulas, if you don't do it, then the formula will plus and minus will all change. Okay, so this is the 1. So if you, and this is the one that's going with speed u, and this is the x direction, so u I hat, and these are the formulas for that. Okay. So if this thing saw events at the origin, 2 events, so in this frame the time difference will be the time difference from this frame to that's like 2 time. So delta t1, 2 clocks, and delta t2, 1 clock. That's the formula we need, and that's going to be gamma u, right? Always going to be like that. So if I find gamma u, I'm done with finding u, right? So delta t1, it says 11, and gamma u delta t2 is going to be 5 seconds. So if you messed up, gamma has to be always greater than 1, greater than or equal to 1. So gamma u is 11 over 5. So let's see what do we have. 1 over square root of 1 minus u over c square equals to 11 over 5. So square root of 1 minus u over c square equals to 5 over 11, and then this will give me u over c square is 1 minus 25 over 144. No, let's call it 12. Okay, I meant to have 12, not 11. Okay, 12, make it 12. So 144, so that we can actually get a so 144 minus 25 over 144. So this is 9. Actually, we could have done 11, but I had something else in my mind. 1 over 144. So u is square root of 119 or 144 times speed of light. So that's the part A. Okay. To answer part B, often helps to draw what So if I draw it, so first event happened when they're right on top of each other, and then the second event happened when this guy is over here. Okay, so if I know the time it took to get there, then just multiply by u, and that will give me the change. So this one is basically you are saying is 12 seconds. So in here you have a t1 was 0, and when t1 was, so we had a clock here, and t1 here was 12 seconds, right? So it's in this frame, in my frame 1, what's the distance? Well, it's going to be u times t1, and that's going to be square root of 119 or 144 times c times 12, and c will be 3 times 10 to the power 8, so that many meters. So that will be how far they will be separated, because this is actually going pretty fast if it's that much time difference. Okay. All right, so this is example 1. Okay, so again, it's always good to write down first the rest frame. So this is the frame 2, and this is the x-axis, and stick is say L0 and alpha 2. So this is all fixed. There's nothing moving here, everything at rest. And then you should draw the other frame frame 1. So whether this guy is moving with that and this guy doesn't matter. We have a formula for that guy, so I'm just going to use this guy's moving UI hat. Or you can always convert this guy's moving minus, so this is the same thing as this guy's moving with a minus UI hat. So if you wanted to do formula like this, you would have you'll have this guy moving U minus UI hat. So you'll have this scenario given by these formulas, right? So rather than have all kinds of formula or kinds of situation, just stay with one and then you'd be fine. Okay, you can always translate one answer into another. So how do I address this? What's the angle? Oh, this is theta 2. So what's the angle that this will be? So what I'm saying is you are going to have two different pictures. One, let's look at t equal to 0, x1, and then this guy is right on top of that. So this thing is like that, and this is in frame 2. This is what it looks like in frame 2. And if so, in frame 2 you have you can see this is L0 cosine theta 2, and this is L0 sine theta 2, and so this is y2 and y1, and this is x2, right? So the only thing that's going to be and this thing is moving with respect to u. So from here you can already tell that this length will be same in the frame 1 and frame 2. So L1y will just be L0 sine theta, and L1x will be this one compressed by gamma, right? L0 cosine theta 2 over gamma ui hat. So if you have some other situation, you just have to, because u is as a u square, it doesn't make a difference, right? Plus and minus, and so the angle will be the ratio of these two, right? So tangent theta 1 will be L1y over L1x, and that's just going to be sine theta 2 sine theta 2 cosine theta 2 over gamma, and so this will be gamma u tangent theta 2. So theta 1 will be arctangent of gamma u tangent theta 2. So this is an application of that is a length is contracting in the direction in which the relative motion is taking place, but length is not contracting in that direction. Okay, so here's another problem. It's very common to see in astronomy, redshift. So here's something I picked up just by doing a search. So Z is a measure of redshift, and it's defined as what you observe and what would be for the same light if you were to do this experiment in a rest frame, like in the lab or something like that. So okay, so this is it's very straightforward application. So you again, there are two frames. So here is a rest frame. This is G11, this, and this is moving with some speed in the line of sight, and there may be a transverse speed which will not be picked up, and then we have this lab, and it emits certain thing. So the lambda observed, lambda rest. So this is lambda 2 is lambda rest, and so we want lambda 1 is the lambda observed. Okay. So you notice over here that this is just equal to lambda observed over lambda rest minus 1. Usually you just use the letter O for that, and you just omit that. So this is lambda 1. So all we want is lambda 1 over lambda 2 equals 1 plus z, which is 12 here, and this we already know. This is going to be square root of 1 plus u over c. This is u over c over 1 minus u over c, and this has to be greater than 1, right? And this is equal to 12. So we need to solve for u over c, and so we just call that some x equals to u over c, just for solving. Now square it, and it's going to become 144, and so 1 plus x equals to 144 minus 144x, and so if you bring this down to 145, 45x equals to 143, so x equals to 143 over 145, so u equals to 143 over 145 c. It's very close to the speed of light. This galaxy is really receding very fast. Okay, I'm going to stop here. We have had a full hour of discussion and 3 examples. Hopefully this helps you out. Take care and bye.